Hello, everyone. So here we are again. Where's my camera? How do I undo the camera here? Uh-huh. Storage and video. Oh, there I am. My coffee is almost ready. So everybody made a snowman today? Snow day. Gotta make snowman a snow day. How about some snow angels? Or am I just gonna talk to myself while you guys quietly hide? That's fine. I
Don't worry,
think.
Dr. Deal. I did a snow angel yesterday.
Oh, excellent. Thank you. Great to hear. Great to hear. You would have thought there you would have seen more snow angels during the Broncos Patriots game at the end, at least. Seems like that would have been an opportunity. All right, it's time to go. Okay, so it's being recorded, and I don't have a compass here at home with me, so that's a flaw in the system. We ended the last class. I put some extra things here at the end. If you remember the last class, we started graphical synthesis where we were making these rocker go back and forth. Now we're going to continue with a little bit more complicated, but not that much more complicated uh, synthesis. I'm plowing through yesterday, the last Wednesday's videos here to get to the end. Nope, I think I missed actually. The one I meant to put up was class three. I never got to talk about the things at the end of class three, and I meant to try to squeeze that in the last class. So let me come back into here. If you remember, so two class ago, about I guess a week ago, we talked about DC motors and how we would, you could, there was a few different varieties, but we're basically just only going to use the permanent magnet DC motor, and their speed versus torque curves and would be something that we would want to match to a system. Um, I didn't get it. So I mentioned this is the new motor, geared motor. It's got some planetary gear in there. I think it's actually two-stage planetary gear inside this motor. Uh, I wanted to mention that the output of a mechanism like the ones we're going to build, its torsional profile usually looks something like this. All right, so here's a simple link, and this is done in both in SolidWorks and MATLAB, and hopefully at some point I'll be able to measure the current directly from the motors, and we can see how closely they resemble as a function of torque. Here is a the also the output that you might expect from a crank slider. This is a crank slider that's accelerating, by the way, which is done for a particular reason because I was trying to match the results of an example problem that was both had a velocity and an acceleration. The crank did, so I had to make the unit so that there was a particular spot that coincided with the orientation, velocity, and acceleration of the crank. Um, and then finally, here's a four bar, and you can see that this is what would be anticipated as the driving torque that would create this profile, right? And this was actually was decelerating. That's why it has some of the look, but you can see that it's fluctuating greatly. That also brings up something from dynamics. This is covered later in this book. that we have. And we will talk about it at some point where this fluctuation of torque is something that you usually want to try to handle by way of a flywheel. And there's a discussion of that in chapter 11, where you could see here's an example where you have a fluctuating torque that's resembling some data that you got from someplace. Like it could have been from SolidWorks because you could see our torque was fluctuating too. But you want to try to match that to a motor or pick a motor that would be sufficient for that torque. Well, that's really kind of difficult when the torque is all over the place. Having a flywheel will definitely help in the real world applications. So you could see adding a flywheel, if done correctly in here, you could get this. These graphs are the same, and you could take a look at the uh, 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 the scale on here. It goes from 0 to 70 right here on the left one. And then with that great fluctuation that's even going negative on some level, that means that there's that instead of producing torque, it's requiring torque to make that portion of the turn of the 360 degrees that you see on the x-axis. And that if you size the flywheel as they've done here, this is the anticipated behavior where it has the same average torque, but the fluctuation has diminished. It is impossible to totally get rid of all the fluctuation, but you minimize the fluctuation. So anyway, that was something that I wanted to bring up and mention because we spoke about motors, and I also wanted to mention, well, we were going to try to match a motor, or we've already picked a motor, so we're going to see what the results of the motor that we picked are. Might even consider at some point trying to add a flywheel into the whole shebang to see if we could smooth out. But we probably won't this semester, but it would be a cool thing to try to add in there, see if we could smooth the thing out once we've measured it without a flywheel. And there was a question. I think I've gone long enough, ate up enough of class number. This is class 5 with some other content, so I won't add this. We'll talk about this as an add-on to an upcoming class. But there was a question about what about things of more than 4 bars. So I made up some slides about 5 bars and 6 bars coming up, so we could do that. So for the topic du jour, I'm going to get rid of the 4 and the 3 here. Let's come back up to topic class 5. We're talking about 4-bar graphical synthesis. Now, I would like to do this with a compass, but as I've mentioned early here, the class started, I don't have a compass with me today. Unfortunately, I left all of them at work, so that's sort of a defect in the presentation of material. Uh, so here we are in class 5. We're right on schedule, and we are mostly covering section 3.4. I had that in the schedule as a range, but it's really 3.4 is mostly where this content is coming from. So this is 3-position graphical synthesis compared to 2-position synthesis, which we started in the last class. And I will be doing some SolidWorks implementation as part of that. So let me get that SolidWorks started on my machine. I need to get where's my Cisco? All right. I'll get my Cisco going here, and then I can start SolidWorks remotely. I think it started. Looks like it started. The printer didn't. Printer gave up. Okay. So that's going on in the background. All right. So the bottom line for doing 3-position is that we look for the center of circles that will pass through the connection points. And by doing that, we can create the 4-bar, right? It's as simple as that. As part of this, I wish I had drawn this in place. So let me do that now. So you could see that we have like A1, A2, and A3. These are connection points that are given. We can also choose them, right? So that's also there'll be some discussion about, well, how do you choose those points? Well, that's part of the synthesis. You can think of it as trial and error, but there's some like maybe some strategy in your trial. There's an infinite number of positions that you could choose to achieve a motion, but making some decisions. So the decision's been made for us. So here, if we could find a circle, I didn't do a good circle. That was not a good circle. I won't try too many. That's one of the reasons why we need a compass, right? If we're gonna pass through. All right, so that not a great circle looks like a lemon. Um, don't judge me too harshly. And then we do the same thing for these others right here, some other location. Boom. I'm drawing on a vertical surface, so this is, it's not easy. So anyway, that's the big idea. If we could find a circle that passes through, we could find the center of a bar that goes through it. I'll come back to purple. So here's like maybe this the center of a different one right there. I'm not sure. They could cross or they could be open. We'll see that there's a lot of issues that could possibly come up. All right, so this is what they're showing from the example, the solution manual for this, and then we can also add a driving dyad onto this thing and make it go back and forth, and voila, we've made a 6 bar, and this is actually, I believe, a Watt 2 6 bar. Might be a Watt 1. I didn't double check. It could be, but so here is an example of 2 point. So like in this problem, problem 522, which is I know we're in chapter 3 right now, but chapter 5 is like a parallel chapter because in chapter 3 we're doing graphical synthesis, and chapter 5 we're doing analytical synthesis, which is a little weird because in chapter 4 is analytical analysis, which is the weirdest word phrasing. I don't know, analytical. I'm looking over here because I have two monitors, by the way, and I know it's a little weird. I'm not looking at you. I'm looking over here. So anyway, this is a problem where they've said to go from this position to that position right there. But here's the consequences of doing that. We pass right through that block. Now, I guess we could probably cut off the block right there. But instead, and here, by the way, up in the right-hand corner is the solution to that. You could see. Um, but here it is. Instead, here's problem 525, where they say to go through all 3 positions, and you could see here's the solution if you follow the process that we're about to find those. And you can see that it goes through all 3 positions right there. You can also see that they've made these little vectors right here to kind of give you an idea of the orientation. So this box is also rotating as it's being brought down, which isn't, maybe that's fine for whatever reason that you're moving this box, but might not always be the thing that you want to do. All right, so here's the first example of the 3 position. And it's kind of weird that they chose this. And this is like the main example that they have in this chapter. And it's not a very good example because you'll see in a minute, it's got some flaws to it. But they use it on purpose because they do some adaptations onto this to try to maybe improve it because you don't necessarily like the result of this example. So this 3 positions here, we're going to here's where they're showing a little bit more of it, and this kind of already shows the solution to it, which is a spoiler, right? But here's the big idea: we want to try to go from each of these 3 positions, move between them. So just like we did with 2 position, we draw lines. You could kind of see them faintly. I've drawn them in there, but we draw a line in between C1 and C2 and between C2 and C3. And then we draw perpendicular lines through the center of those new lines, and we see where they intersect. And then we do the same thing for D1, D2, and D2, D3, and we see where they intersect. Boom. And those are the grounds for this mechanism. And so we could see And we label them O2 and O4. Boom. And so that's what the thing is supposed to do, right? And of course, those are the centers of circles that pass through all 3 points. That's all it is to it. So you can kind of like see I'm going past through the slides. So you can see it's doing the thing that it's supposed to do. And here is an animation of the results. Boom. Well, that's all well and good, and it sounds like it's fine. Something to keep in mind is when you're adding a driving dyad, you want to pick maybe the one that has the smallest angle to it if it's possible, right? So that you can and where you pick it along along the center right here is up to you because you can pick it up higher or lower. But of course you want to make sure that you haven't it's long enough so that you would be able to have enough overall moment from the driving dyad to be able to push this thing back and forth. But you can see in the next animation here, I have just tweaked this little guy up just a little tiny bit. Now, I did it so you could see it enough. You could see it enough, but you can almost see from the problem here that they're almost in line with each other. They're practically in line with it. That is to say, the coupler and the rocker, if we're going to call that the rocker, they're almost in line with each other. But what if you tweaked them the other way? Well, you have this like you have inherently have a change point in there, and because of that, it's going to decide that instead of coming downwards, it's going to go upwards, right? So that's not a desirable trait to have in a mechanism. So we might want to go about trying to find another solution to this. And so that brings up the next example. And I haven't covered this example before. This is my first time covering it. I thought, this, because I split this class used to be like the last class we had and this class used to be the same, one in the same. So, but I decided, I'm going to split them up. And because of that, I'm like, I think I'll have enough time to also show an alternate approach. And this next the example after this one as well. I haven't added that one either. So I've added this one and the next one as examples. So herein we have chosen new grabbing points. Like this is the thing, this rock. I don't know why we wanted to move it between these three positions, but we did for some reason. And we established these are the three positions. But what if we grabbed a hold of it in a different place? And that's up to us, right? So we don't know that that's the right place, but you can work backwards as I'll try to show you in a real example that I previously did. So you could kind of see, oh, well, the attachment points weren't great. Maybe that's what we just found out. Those weren't great attachment. Let's try other attachment points, E and F. So if you picked these two spots, we have we've definitely moved. We didn't really change the general shape of this thing. We kind of still needed to have the rocker up high and the let's call it the crank down below. It's not really just another rocker. Um, but we were able to shift it from them being in line, right? So that's the little tweak that we made. And so that's the idea. Well, we've just shifted these two down, and we did all the the lines in between them, and then we made perpendicular lines, and that established the ground. And then we did the same over here, boom, boom, and then that established this other ground right here. And remember though that there's legs going. I've made this mistake before. Is I've just used these dash lines as the ones that I followed them. I like just forgot. I'm like, no, no, no. We need to go from that ground to our attachment point. So we have to go from here to here, right, with a leg. And then I didn't even draw it here. I guess I kind of forgot it here. Like the other leg would be right between there, right? So now we've made ourselves a four bar. Now that's the four bar that we've just made. And of course we could attach a driving dyad onto it. So there's the driving diad and the extended. So there's the crank and there's the coupler of the driving diad. This is the right, the a partial of the rocker slash crank of the primary four bar is now just a segment of it is the rocker for the driving diad. And then of course this is the ground right there. So you can kind of see in this animation that it does go through these three positions and it doesn't have that same problem that it did in the previous example, right? We were able to get it to go through those three things. So that's one of the alternatives to that first problem. The second one, all right. So these are actually two examples in one, and I don't know why they split them in half. This is a little difficult to follow, so hopefully I can do it in such a way that it eases. I think if you read the book without seeing this, it'll be a little confusing. But hopefully, me working through this will make it easier to read the book. But you won't necessarily understand it immediately upon me describing it. I think that might be the case. Maybe, maybe you're quicker than I am. I found it a little confusing first. All right, so here are the three positions that we originally had and we would like to find a specific ground position. Okay, so we want to we're not going to find a ground that does this. We're going to find a mechanism with this ground that will move through these 3 points. Well, they're like, well, how do you do that? Well, you kind of use the like an inversion and then an inversion of the inversion. I know that sounds a little weird, but let's just take it on faith that it can be done. The first thing is we might like go, um, okay, so what if we had to pick these 2 points? The first thing to do is take a look at points two, at the C2, D2, and we're going to say, well, what would what is the ground as related to C2, D2? Boom. So we use these two triangles. We said these, so we're going to use these two triangles to find relative grounds to position one. So it's like, okay, if this is the gonna has to be the ground, O2, O4, let's look for an O2 prime and an O4 prime as related to point one if point two was like the standard, the reference. So we're going to take those two triangles. They're showing them, by the way, with little compass marks because that's the way that you would do this graphically is you would get your compass and you would find maybe where O2 was with respect to C2, and then you would move it over to C1 and you'd find where this O2 prime would be. So in the next graphic I'm about to see, I'm going to move these two triangles from their spot over to position one. So okay, so that those are the triangles. I set them over to the side, and boom, right there. We've just now moved them. And by the way, they hid the other two's positions right in there to make it clear. So I decided, okay, yeah, I'm going to discard this. I'm going to go back to the slide I was just on, boom, and show you, all right, because I've drawn these now and I'm going to bring those over to here and I'm going to bring them in the right orientation. I'm kind of guessing so that they're right there. Okay. This was the part that made it unclear for me right there. Okay. So you see where that new red line is? That's where that O2 prime and O4 prime is. It's because I've just used these triangles that I just got from the two position. I've brought them over to the one position, and now I've labeled them as O2 prime and O4 prime, right? So I'm going to move this guy back over, right? Boom. So now we have a new red line. We have O2 and O4, and then O2 prime and O4 prime. And now we're going to do the same thing, except over onto position three, right? So right here is position three, right there with triangles that we've just made. And so that's where the O2 and O4 was relative to it. And so we are going to move that back over to the one position and create the O2 double prime and the O4 double prime right here. So this is what we're going to do. We have that these triangles. We're going to move these over to here. Whoops, I didn't mean to do that. And we're going to rotate them just the right amount. All right, boom. So now we have this new red line connection, and you can see, boom, that's O2 prime, double prime and O4 double prime right here. So there it is. We moved those triangles, moved them over to here. So I'm moving this guy back over. All right. So now what do we do with that? We have C1, C1 and D1. That's just for reference. They could have also put the C2 and the D2 for reference. They just left them out for some reason. And the C3 and D3. They also left that out. So we have these new positions. They've decided to give them new letters, E's, E1, E2, E3, F1, F2, and F3. I don't know why they bother to do that. But we're going to ignore our C1 and C2 now, and we're going to do the same thing that we just got done doing in that previous three position example. So now we have these grounds, right? So what we've kind of done is we kind of inverted the problem. Like, and so instead of being you know, try to find the grounds is like now get the grounds and get new grounds and try to find grounds for the grounds, kind of inverted. But we try to use that, and from those new grounds, you'll see that those positions they're calling them G and H that we got by drawing connections between these right here. By the way, we won't be doing this, but I'm just thought this would be a value added thing to this three position. So don't worry. If it is confusing, we're not going to be doing this. But you could if you want to, if a practical problem came up where you couldn't use the regular grounds. Here's like an alternative approach. All right, so here we go, where we have we've created this mechanism to do this thing here, where we're going to be able to move E1 and F1 through the three different E and F positions. All right, so that would be the end of example 737, which would make no sense. So, like, why did we bother to do it? Here's where we start to close the gap, close the circle of why we would do this. Right. So here's that mechanism that we have right there. Boom. I think you could. Oh no, actually, we've inverted it, right? When we instead of being E1 to F1, we have we've turned that into the ground, right? So this was the new mechanism that served no purpose at all, but we're like, okay, well, wait a minute. Let's instead of that E1 F1, let's that was the remember that was the coupler. Let's make that into the ground, which you'll notice was the same thing as our O2 O4, right? Going backwards. So that E1 F1 was our ground, was the desired ground. It's the coupler here. Let's take an inversion of this and make it the ground. Now, this is the new mechanism right there that we can make an extension off of the coupler and it will go through the three positions that we want to. It's kind of a neat thing, right? That you really, it's a weird looking coupler. We've made an extension onto the coupler, but this will go through all three of them. Not a great solution though, in my opinion, and here's why. Because I went through here and then I built it and then I animated it, right? So here's what it's supposed to do right there. And if you go through, we got to look through these three positions that it's supposed to go through. And first off, it doesn't go through them in order. And if you, let's see if we could stop them. All right. Right. All right. So it passes through that. It goes from one to three to two. Of course, I could have had it tell it to, I could have told it to rotate in the other direction. But then it goes to, then it goes to, whoops, let me do it again. All right. So it goes to three, comes downwards and comes back up into two. I did it again. I'm trying to hit the right button right there. Uh, right up, boom. So it goes to the second position. Ah, come on. And then it goes back up to the first position. So not a great solution, but it is a solution that goes through these three things. Um, just interesting. Okay, so back on track to the thing that we will be doing repeatedly and on exam one, right? So that was three position. The first all the way back um, to this example right there. This is the main example, right? This is the example in the book. And as I mentioned, not a great example, but here the next one we're doing is a standard example that we will do repeatedly. So we should pay it. You can just go ahead and purge the rest. Everything you just heard, you could purge it out of your brain. And starting now is like the most important part because we will be doing this repeatedly. So here is one that gets done over and over again. It's problem 348 out of the book. They use the same problem in chapter 5, so that's 525 out of the book. And here is the solution here at the bottom to this. By the way, you can ask a question at any time and we can interact, just so you know. That would be interaction would be nice. You could hit a chat. I don't know if I remember how to respond to a chat. Oh yeah, I could do that. Um, let's see. And by the way, everybody can see my screen, right? I need some human interaction here. Yes, I got a thumbs up. Yeah. Hey, look, Josh is showing us what we could do. Yay. Thank you for thumbs up. Sometimes I would get lonely during COVID. And so what I found are these little things right here because no one was responding to me. Oh, and is it broken or is it switched off? Oh, I bet the battery's dead. Well, I got several of them, so one of them probably works. I need positive reinforcement. I think most people do. So anyway, let me go work through this one. I'll quickly show you what I'm about to do and then do it in SolidWorks. If it doesn't crash, if it does crash, then sadness. All right, I don't have a crying one. Although this one has little tears on it. As you can see the little tears. See this guy tear? But sadly, he doesn't have an on-off switch like the other ones do, and I'm pretty certain the batteries are dead. Let's see. Can we get the batteries to no. Mm. So much for Energizer Max. Um, all right, so you can see here where what I've done to be able to make. Ooh, I saw some chats. Extra credit if we turn the button into a mechanism. Yes, absolutely. Down with that. Yes, absolutely. Um, okay. Oh, I like the rooster. Thank you. Can I tell an off-color story? So it's being, wait a minute, it's being recorded. I think I can. We were visiting Kauai. Has anybody been to Kauai before? Got any Kauai people, visitors to Kauai, the Hawaiian island, Kauai? No, no, sorry to hear. Well, I guess there was a hurricane, I don't know, a long time ago, and all the chickens got out. So many, they were like, this is no, there's no way we're ever getting all these chickens out. So they just let them run loose. So everywhere you go, and then in the morning, you hear the roosters, big time, big time. Yeah. So it kind of came their like mascot. So you see pictures of roosters everywhere. And so, like, walking down from the hotel to the lobby, there was like this little gift shop that they was strategically placed. And I saw some socks, and they had rooster socks, so I bought some socks. I think I'm gonna stop this. I'm starting to rethink this, second guess this story. So this story is on pause. I'm not recording this. All right, that's fine. Anyway, coming back. What the idea here is we do these connections. So our connections are between, whoops, what happened here? All right, let's see something. I just moved something here. Let me go back. I'm a little nervous. What happened there? Okay. Um, Purple. Here's our connection points A1, A2, and A3. And I make my connections in between them, and then I make perpendicular lines from them. And lo and behold, boom, we got a connection point. And it's kind of an awkward looking connection point. You don't always get great connection points. That's one of the reasons why you might want to attempt the uh, the thing we just did in the most recent example where we tried to force the connection points onto the thing. And it might be something we want to do. And then we also go to, oh, I did it again. Go ahead, back. Um, and green. We go between B1, B2, and B3, and we find kind of hard to see in here. It can be kind of confusing right there. So we're able to find these two connection points for legs, and then between the legs, we are able to orange make uh, uh, make legs for between those connection points. We're able to make legs, and you can see that it would that one would have to move a between A1 and A3 and go through this arc right there. That's a pretty large arc for our driving dyad, but we don't really have that much choice in here. We'll see later that we have something that can alleviate a little bit, but it's still you still have to make just like the very first example in two position had to go through an arc, that looked like it was maybe like 30 degrees or so. Now we have to make one that's uh probably 150 degrees, which is a kind of a large movement right there. So there you go. I had actually made these two guys to go through it to find that center, and then between those two and to find that center. And then, of course, we made those two legs. And you can see that what we've done is made circles whose centers are at the ground points. That's the gist of what we've done. I'm repeating, but that's okay. That's what's it's good for learning, right? Um, and then so here's the driving dyad. And here's something I've done in this case is sort of a little trick, but it's not a trick. Instead of trying to force the driving dyad up above, I can make an extension onto the leg. And I chose this one and this one instead. And so like I extended their legs out, and then I made the driving dyad connected to that spot. So I didn't have to position up higher. It's just a little bit of a trick, but also useful if you look at the solution that Norton created. That's what he's done. So I should have made this one probably the second example so you could see that little trick in there. Boom, 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 right there. And so now here is the solution. You also notice that if I put this on here in two different positions, you could see that I kind of needed to make a little divot right here to be able to manage the fact that that leg was going to hit the other pivot. So it doesn't have to be straight, I think I mentioned that in the last class. The leg doesn't have to be straight. So here you go. Boom, onto the thing, and you could see kind of better how they couldn't manage right there, and they end up crossing over too. That's also another thing of note. Well, not quite crossing over. I think the next one crosses over. So here is the one where I'm going to do this one in SolidWorks all the way through. But here is the solution to it. So that and hopefully you'll be able to do these, right? You'll be able to make something along these lines. That's the big idea. So right there, I've made the connection between A1 and A2 and A2 to A3 and drawn those perpendicular lines through the centers. That creates that ground. And then I did the same thing for B1 to B2 to B2 to B3 and found those. So created a center, right? So I think I animate this. Boom, 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 boom. And so there's the leg that goes to A1 to that first ground and B1 to the second ground. Making the driving dyad, I've chosen to go up to right here. So I made an arc right to there to make that happen. And then so this is one, and you've seen this one printed out, right? But actually, you've seen both of those printed out, both of those examples. I'll bring them with me in next class as well. Um, as a real thing, it's nice to be stay in one plane. It has all kinds of complications to be in two plane to in three dimensions, right? Um, for this one, like if we wanted to actually just there would be a lot of cantilever onto the ends of this link to try to keep it down there. And there's sort of a desire to, well, then let's just make it symmetric so we could hold it, so we don't have to cantilever it. But now, quite often, a lot of times we'll have a problem of twisting and racking. Um, so there's some concern, in reality in that respect. You'll see that in my, I think I've already shown that because I brought in my uh, the, liquid pouring device, um, kind of had that problem. So just be aware, like when trying to take one of these planar things and make a three-dimensional functioning part out of it, you have to find a way to address those issues. And I think some of mine, you could even say, was quasi related to that same issue I mentioned in a practical considerations about the bearing ratio, right? We don't want to, making the aspect ratio, if you will, of the connection points. If they're side by side, and then you try to go in that direction, that could lend itself to that kind of twisting motion. This is a cautionary tale, but I'll wait for the cautionary tale until we have gone through an example all the way. I'll start with a part, and it's not looking good here already because we're taking a while to start a new part. Why are you taking so long? Maybe, can I close Chrome while I'm in the middle of it? But in the middle of Zoom, I think I can. I don't know. Not sure if they're interrelated with each other. Okay, so this is looking bad. This is looking real bad. Is anybody like already like are you guys still there? Anybody there? Give me a thumbs up. Give me a rooster. There you go. Okay, cool. Oh, or a yeah. I like the uh what was the name of that video game? I forgot. Space Invaders, right? All right, this is scary that doesn't work. Let's see if I can get rid of him. I should be able to get rid of him. This guy's we're going to be using motion gen in the next class. This is a textbook that was open. I don't know if I think I can close that. I don't know, but it's not working, and I don't know what to do now. And close this. Don't need that open. Don't need this open. Don't need this open. Huh. Why you know work? Don't need you open. I don't need my email open. All right. Don't need you open. No, come on. I should just close that. All right. Why aren't you working? Mm, all right. We're gonna try again. I still have my Cisco going, right? Cisco, yeah, you're going. All right. It's not my fault, I swear. Yeah. Well, while we're waiting for that, let's get something done. All right, so here is a cautionary tale. Um, I didn't assign this one, but I made this possible as one of the projects for project one. And then one of the students came to me and said it was acting really weird. I'm like, you sure? I don't think he. Yeah, yeah. Norton went ahead and put this guy in here. You could see this is the solution right there. And by the way, for the project, I made the solution manual available for the one for some of these. And I thought it would be fine. But this is what happens. So check it out. Boom. Look at that. They're passing through each other. And also look at this piece right here. Boom, like there, it's tilted it upside down. And right there, it's completely messed up. And you're like, well, wait a minute. But if you look at it closely, it does complete the links did what they were supposed to do, which is to make a circle that passes through A1 to A2 to A3 and from B1 to B2 to B3. But you look at this thing right here, and according to this message, it says, unfortunately, although the solution presented appears to meet the design specifications, a simplified cardboard model, he's old school, man, cardboard, will quickly demonstrate that has a branch defect. That is, the first position shown, the linkage is in the open configuration, but the second and third positions are in the crossed configurations. The linkage cannot get from one circuit to the other without removing a pin and reassembling to after the moving vision. The remedy is to attach points A and B to the coupler and not to the joints between 2 and 3, links 3 and 4. And I have no idea what that last sentence means, by the way. I don't know. But anyway, but it was right there. Let's see if we can't get this guy moving along. Okay, all I want to do is start a new part. How hard is that? Oh, I just heard a thing go beep, beep, ding, ding. Oh, there it is. It did it. What was the notification there? I don't see. Sometimes it's hidden right there. Okay. Let's we could get our fingers crossed, but I don't know how much we've just wasted a whole bunch of time. All right, so in the front plane, we're gonna do that tools down to um and I recognize that this thing's taking a long time, so we're going to try to for the exam as was suggested that we get a computer lab to be able to do the exam. Let's see, which problem are we looking at? We're looking at this guy. And we don't have to make it scaled, but we could. It is possible, but it's with this tool. Oh, and by the way, this is supposed to be in millimeters, so I've just made a mistake. Okay. So you can't change in the middle. You got to go back into there. Let's go to edit sketch. Double click on this. Oh, you can almost see it. It kind of moved. It kind of moved. You could drag. Oh, there it is. Uh, oh, oh, there he is. Okay, this thing is a piece of junk. Let's see if we can get him right there. Boom. Oh, still not great. He's still not good, but we're gonna get it close. That's our goal. And I was able to get that one pretty easy. But it's not something I'm gonna require you to do, is to make it, at least, especially not during the exam, to make it scaled. Another thing that you can do if you wanted to make it scaled is when you're not see, we're still in the sketch, but we're not in sketch picture mode, is that you could go to here, make a sketch here, and let's see, make this 167 and make this 180. Get out of the dimension. Now double click on here. So we're into sketch mode here. Oh, no, I don't want to do that. Whoops. I want to do this. You just drag him over to here, and you can see that we are not doing a great job of being in sketch mode. But we can disable and enable this tool again. Oh, there you go. Oh, see, I wish I could zoom in while I'm doing this. It'd be so much better. Boom. And then make this 167. Boom. You could probably iterate. We got pretty close, and that's going to be good enough for us. We get out of this, we got out of this. So we got pretty close to making it happen. So I'm not going to mess around in that sketch. I'm going to make a new sketch in the front plane, and um, I don't have to do the points, but a lot of times I like to. I'd also point out that there's in some of the math that comes up later and some of the examples, they like to include these precision points right in there and form a triangle off of the coupler, right? So it can be confusing not to pay attention like early on to the precision points. So just we're not going to bother with them right here, but for lots of problems, they would do something like this right here. Boom, boom, and then push that up to right there and then move this triangle around, right? So it's just a good thing to know about. So I'm gonna set and fix these points right here. Boom, boom. I'm gonna fix them, and then I'm also going to uh I'll do this in stages. I think this is gonna it's better to do this in stages, like as I'm doing it right here, than to try to keep it all in one sketch. Trying to keep it all in one sketch can have things move around a lot more. So I didn't bother with the fixing of the things. Because I'm going to keep this as a separate sketch. So I've made the attachment points basically a separate sketch. I think that's easier to do. And now I'm going to do the main thing that I was that we our main scheme, which is to go from A1 to A2 to A3. And I could do that same thing for the B's, but I think this is just a little bit easier. I can't find the center. Where's the center? There's the center. Okay, so I'm purposely not making it perpendicular right now. Where's the center? There's the center. Okay. And then I can make the perpendicular afterwards. Perpendicular, and then get out of that and then grab that one and that one together at the same time. Make them perpendicular. Boom. All right, so there is the first ground point. And now I'm going to do it for the second one. Go for the B's to B. Boom, boom. Escape. Now I'm going to go from the second here. Boom, there's the middle. I can put them anywhere I want to. Just don't accidentally create a relation. Boom. And now I can make that hold control. So I get both of those, make them perpendicular, grab a hold of that, grab a hold of that, make it perpendicular. Boom. And now I've synthesized the main four bar. I will now draw in as solid lines. I only have to do the A. I'm going to go from A1 to the ground and from the ground to A3. So now I know this is the arm that we're going to connect a a driving dyad onto. I'm going to take a circle, and now I need to make a choice at how large, how far up on that rocker we want to make the driving dyad. So I went to right about there. I'm making them a construction line because it looks, it's like a easier to keep track of stuff, to not have too many solid lines in here. Um, I'm going to find the connection. You could see that little relation is turned into like an X looking thing. Another one right here. Okay, got it again. And I'm going to extend that line. I'm going to make a line there, and I'm going to make him coincident, not coincident, collinear. And then I'm going to make a solid line from the center to over here. Boom. And then I'll make a circle up here. Boom. And make a solid line. I don't know if it matters, but I'll go ahead and click on that. Click on the edge and make him coincident. All right, so cool linear. So the thing that I can do now is I can decide on a lot of things by way of like moving this around. Like maybe I don't want the crank to extend beyond the box, but I do need to worry about that Grashoff thing. Um, and I wouldn't want to connect onto that link to be too small. So there's a certain amount of movement decisions that I have to make about this. So I'm going to go ahead and stick with about this connection. This is a pretty wide sweep. You can imagine, you can also think of we could even put them in here if you want to, just for reference. Although right now, because there's not anything dimensioned, whoops, I didn't mean to do that. I meant to do this and this and make them collinear. If you were to dimension this, you don't want to, but you could have this right here. This right here is the transmission angle of the coupler in this furthest position right here. The coupler as it would have to be up lifting up the rocker of the main guy, which would probably be pretty heavy, right? It's probably in that position. But it's going to need to lift this thing up. So this is a consideration, is that particular dimension. But we're going to go ahead and leave this, and here is the main thing, and the main operation that we end up doing. So I think this is, let's see, I'm going to come back down to, ooh, good place for this. Unfortunately, still haven't moved it over from the University of Hartford SolidWorks. I will at some point. So this is class five. So I'm gonna go class, demo, and ground. So I'm gonna save it five. Well, I'm gonna save it once, and then I'm gonna save as five times, um, and leave it open. And hopefully this won't like bog down my computer tremendously. But I did see that I am jerky. So I'm not sure. You guys can still hear me? Can I get thumbs up or whatever? I think my computer's really slow. Okay, that's looking. I don't know how many thumbs up actually just went up, but it looked like there was like 5 dozen. So um usually this goes like really fast, but the computer is hating me. I think I should probably bring my Yale laptop from now on if I have to do a remote again. But I didn't think of that on Friday. All right, so this probably is going to take too long to be able to do and finish out class. February 23rd in the syllabus. What does that mean? All right. So anyway, we want to do that save as a copy and open and you can give them a different names. I usually just go I only call the crank the one that's connected to the driving diode and you leave it open. Why is it going so slow? I need to I need to purge this computer. When is the exam? Oh, I see. When is the exam? Late February, right? Yeah. Thank you. Yeah, it should be still in keeping with the syllabus, but I do need to figure out the hmm, a room so that people don't have to, aren't going to be limited by their computers. That's not fair to be limited by your computer. We also need to discuss like when it can start and when it can end. Oh, come on, guy. And so we usually what I would do is go coupler one and coupler two and rocker one and rocker two. And after I'd done that, so that would be six total saving of the same sketch. And I'm moving now. Okay. Oh yeah, so we want to keep the original open and don't ask me again. All right. It seems to have caught up. But normally you would be able to do this like really fast, like boom, boom, if your computer wasn't like, ugh. I could do usually the thing that I'm describing. It usually takes me somewhere between a half hour and 45 minutes to do on a good day. This is not a good day. I would even like save myself some time by making that rocker two. Hmm. And we have 13 minutes of class left. This is exciting, right? Exciting stuff. I was going to show you a picture of my driveway today because I just got it took me like an hour and a half to plow it, to snow blow it. Because the lovely people, either the lovely people of the town or my neighbor who's got a parallel driveway, put in like about 3 feet of snow for a good section of the beginning of my driveway. So it's nice. Nice to have neighbors. Hey, hello, neighbor. We just need music during this. It's boring. Okay. All right. So I have all of them open. Ground, crank, coupler one, coupler two, rocker two. What happened to rocker one? I must have been dozing off somewhere, or he opened recent. I must have accidentally somehow clicked the copy or save and open or save and close or something like that. Whatever it is. All right. So we go back to ground. It's usually the one that let's start with. I think we're in it. I can't quite see. Yeah, we're in the ground. And I make a new sketch. On this one, you don't have to do this, but th this one already has something that looks like a ground, right? So um, I'm just going to go ahead and make this thing the ground, and then I'll make little circles for all the connection points. Boom, 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 right? And you don't have to make them equal to each other in diameter, but you can. And give it some sensible number. Ooh, he wants to be 5 millimeters. That's about, that just seems like the right size. You can make it 4 mil. I don't care. I don't care what size. Just don't make them huge right there. And anyway, so now we make a feature and it doesn't matter. See, 10 millimeters, it's a little thick, but good enough. And we're going in, I like to go in the direction away from the picture so I could still see the picture in the background. And I like to make them green, completely unnecessary, but I think aesthetics matter. And now we hit save, and then we do the same thing over and over again, right? It's a little tedious, but we are in the crank. Um, we're gonna make a straight slot. I like to make him up in uh, uh, the raised position. So I'm going to pick that position. That's the reason why I drew that line in my sketch to be up to there. There's no reason real to do it, but I just like it. Yes is the answer. I just see in it. I don't know what that means. Okay. Um, and the width of this thing, oh, I don't know. I'm gonna make it 10, although it looks a little, it looks fine. I'm gonna make this the same as I made for the other guys, 5. Um, I could just make I could make a relation between those circles and 5, but um, that looks a little thick to me. I'm gonna make that 5. All right. A lot of times I find that I make the proportions of the thing to me look a little better when this circle is one half the width and also the depth of it is about one half the width as well. That looks about right. We can hide all these other things with the little eye right there. On the ground, I left it in there just so that we can, when we go to make it as an assembly, that's the one where we would like to show up. It doesn't make sense for any of the other ones to show up. They'll be weird because they'll be rotating, so don't do that. And then as I usually like to make the crank red, there you go. Got 8 minutes. Um, well, I was actually coupler two. I'm gonna go coupler one. This is the one I usually consider coupler one is this guy between there and there, right? And truth be told, before I started to make this driving dyad, I probably should have checked to see if it was Grashoff or not, because it's going to be tremendous sadness when this thing doesn't work because I didn't check to see if it was Grashoff, but I eyeballed it and my extensive experience making mechanisms this way. I'm guessing I did it right. Just looking at the proportions, I would say there's a whole lot when designing things where the proportions matter a lot. Like when just from experience, you go, yeah, that looks about right. And there might not even be a way to calculate easily the size of a thing. It was true often with brackets when I had to when I had to size brackets for things. I'm like, how do I know that that's the right size? Well, I have found some guidance before, but quite often it's that looks too small, that looks too big, this makes sense, that doesn't make sense, that kind of thing. All right, so here we're gonna make a sketch and start making getting into these other three. So we're one half of the way through right here, which is good news. Here this is, oh, I said coupler two, right? So this is actually the coupler. So just for the aesthetics of the piece, I am going to make it this way, and I'm not going to spend a lot of time trying to be cutesy with it. Um, Probably going to be ugly because I'm not being cutesy. Boom, but good enough. So here are the connection points. So I need to put those in there and can't stop myself from making those five because, whoops, five. Okay. Little delay in the, come on, five. Boom. Okay. And 5 minutes left. Features, boom. Come on. I'm gonna make this five deep because that's what I had been doing. And can hide all the rest of this and make him something interesting. I think I made him orange on the other one. So might as well be consistent. Foolish consistency is the hobgoblin of a small mind, is what I've heard before. All right, two more to go. Rocker two. I guess it doesn't matter which one's rocker one and which one's rocker two. But still, there's find myself gonna want to go between here and here. I actually didn't draw that guy out there, did I? Yeah, but that's the other rocker. Oh, accidentally clicked the wrong thing. All right, get out of there. Slow me down. Come on. And yeah, I'm not going to be able to make it in time, am I? All right, so I'm going to leave off the dimensions, save myself a second. Come on. Come on. And. Get rid of everybody. 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 Get rid of ever Boom. It's been the most exciting class you've had today, right? Everybody else is probably like, yeah, we're not having class today. Come on. Only one more to go, man. Save. You get the idea. Oh, let me see. Oh, I did doing the wrong thing. Okay. And this this one can go in between here because this is rocker one, I decided. And yeah, we're not gonna do. All right, so with 1 minute left, there's no point in trying to make the assembly. We'll pick up where we left off, hopefully in on Wednesday, and this will be a much more straightforward, interesting thing that you'll be able to do. Let me finish up with um, as we mentioned one other time about the a useful and interesting problem that I have based the project on previously is trying to pour a malted beverage in a way to make a mechanism to do it. And so here's me trying to pour a bottle and the connection points that I've tried to choose as I was doing it. First off, I tried the little black spots, and then I chose the just with uh, using actually PowerPoint to pick these spots and this orientation and find these locations to do the connection points and to make a mechanism based on that. And so this was the mechanism that I tried to make as I've shown in class. We'll talk about it some more, but here, as you could see, the grounds that I ended up picking and the connection points and the driving diet. All right, thank you for your patience and sorry for the technical difficulties. Have a good snow day. Be safe and stay warm. The end. Thank you so much.
Thank you.
Thank you. Have a great day.
Dr. Deal,
Yes.
for your office hours tomorrow, are they going to be on Zoom?
No, I should be in my office.
Okay. All
Yeah.
right.
I'm,
Thanks.
I only did today because I we got about 18 inches here in Westbrook, and I didn't think I'd be able to plow out. And sure enough, if I had woken up in time to plow out, I would have been late to classes.
Yeah. All right, cool. Thank you.
All right, great. Thank you. See you tomorrow. I mean, yeah, tomorrow maybe.